We are now ready to learn how to search for longest passes not only in simple Manhattan-like grids but in arbitrary alignment graphs. Here's an example of a graph, and in this case there is only one way to move to these three nodes from the source, and there is also only one way to move to these nodes from the source. But when we move to this node shown by the question mark, there are actually four different ways to move to this node. Which one should we choose? In this case, we actually have four choices, and as before, we choose the variant which provides the longest path. In this case, this path is the optimal one, and we know that the optimal path from 0 to the shown node has length 10. We continue doing this, and in the end we will construct this graph with every node marked by the length of the longest path, and we will learn that the length of the longest path from the source to the sink is 29. And as before, we of course preserved the backtracking pointers, and that's why we will know how to move back in this graph and find the optimal path itself. As a result, we now know how to construct recurrency for the dynamic programming in alignment graph. If we define Sij as the length of a longest path from 0, 0 to ij, then in the alignment graph, where we have diagonal edges corresponding to the alignment gate, we have three choices. We can either compute Sij as Si-1j plus weight of the vertical edge into node ij, or Si-1j plus weight of horizontal edge into ij, or as S-1j-1 plus weight of the diagonal edge into ij. And as a result, our recurrency for the longest common subsequence problem becomes particularly simple, because the weights of all edges in the longest subsequence problem is 0, except for the red edges that correspond to matching letters. And therefore the recurrency is simply Si-1j plus 0 or Sij-1 plus 0, we can drop 0 of course from this equation, or Si-1j-1 plus 1 in the case I symbol in the first sequence equal to the j symbol in the second sequence. As before, we of course preserve the backtracking pointers for the longest common subsequence, and in this case red edge has weight 1, all other edges have weight 0, and here are the backtracking pointers for our particular problem, finding longest common subsequence for these two strings. And we can move from the final destination backwards using backtracking pointers, and slowly but surely we will arrive to the original initial node, and all passes that are traced by the blue edges represent the solutions to the longest common subsequence problem. To compute backtracking pointers, we have three choices. We can either record a backtracking pointer as a vertical, horizontal, or diagonal edge. And as soon as the backtracking pointers are computed, we can write a simple program that allows us to output the longest common subsequence by once again exploring three choices: green choice, blue choice, and red choice. We have now learned that to compute a scorer at a given node, we need to consider all edges entering into this node. And the initial vertex of each such edge is called a predecessor of a given node. And therefore, the recurrency for computing the longest passes in an arbitrary graph will be the following one. Let's denote S of A as the length of the longest path to node A, and to compute S of A, we need to compute maximum among all predecessors of node A, and we take maximum among the value scorer of each predecessor plus weight of the edge from this predecessor to a given node. So let's try to apply this approach to a simple graph shown here. We start from the initial node, and of course the length of the longest path to this node is 0, and we can compute two other scorers for two other nodes 4 and 6, and now let's try to compute scorer for the node shown by the question mark. There are two edges entering into this node. Scorer of one of them, of one predecessor, is known at 0, but scorer of another predecessor is unknown. Therefore, before we compute the scorer for the node shown by the question mark, we need to compute one more scorer, which is this one. But to compute this scorer, we need to compute scorer in another vertex, shown here. But to compute scorer of this vertex, we need to compute scorer for this one. And to compute scorer for this one, we need to compute the scorer that we have been trying to compute some time ago. So we came to a vicious circle. It looks like a catch-22. We need to compute something that has not been computed yet, but to compute it, we need to compute something else again and again and again. So, and which tells us that the order in which we explore nodes of the graph is extremely important. By the time the node is analyzed, the scorers of all its predecessors should already have been computed. And if the graph has a directed cycle, like the graph we just looked at, there is simply no way to solve the problem, because a traveler may travel along this directed cycle as long as he wants to. And therefore, we limit attention to so-called directed acyclic graphs, or DAGs, which are graphs without directed cycles. In this slide, Batman is looking at a directed acyclic graph and is trying to solve a difficult dressing in the morning problem. And topological ordering of a graph is ordering of nodes of the DAG on a line such that all edges in the graph go from left to right. There are different ways for this Batman to get dressed in the morning, and two of them are shown here, and each of them represents a topological ordering, because by the time Batman needs to put something on, all necessary things already have been put on in this particular case. And there is a simple theorem that we are not proving, but you can try to prove it yourself, that every DAG has a topological ordering, and in fact, for our Manhattan grid, there are many different topological orderings, and two of them are shown on this slide. And after we learned that topological ordering is important, we can design a pseudocode for the longest path problem. And it works like this. We first topologically order the graph, and then we update nodes in the order given by this topological ordering as described on this slide. What is the runtime of this algorithm that we will use heavily in the remainder of this lecture? Well, when we run dynamic programming, we look at every edge in the graph just once to update the node that this edge goes into. And therefore, the runtime of the dynamic programming algorithm for finding longest passes is proportional to the number of edges in the graph. And we are now ready to look at different varieties of sequence alignment problems in biology.